a really interesting issue that came up on quiz 5. Okay, so to remind you, in problem 1, you were given a wave function, e to the I, some number, x minus some other number, t. And you were asked to find momentum, energy, and mass. So the right way to do this problem is you had to recognize, aha, this is a wave with pure wave number and pure frequency. So this must be the k, this must be the omega. And then according to Mr. de Broglie, or Monsieur de Broglie, momentum must be h bar k, energy must be h bar omega, plug and chug. And then we found that in order for this wave number to satisfy Schrödinger's equation, a free particle Schrödinger's equation, it must be that E equals P squared over 2M. So now if you know E, you know P, plug chug, you find M. Okay? This is the right way to do it. And about half of you did exactly that. That's great. I want to remind you that this wave function is a solution to free particle Schrödinger's equation. Why do I emphasize letter A? Because you can obtain other solutions by superposing other harmonics, right? They will have different Ks, and they will also have different omegas. Remember that omegas and Ks are related. So this is equivalent to saying that omega equals h bar k squared over 2m. So if you have a harmonic of wave number k, it must automatically have a frequency omega. And that harmonic is given by omega over k, which is h bar k over 2m. Notice, by dividing omega by k, you are finding the speed with which this wave travels. This is not a quantum mechanics idea, right? Anytime you have a wave, water wave, sound wave, seismic wave, quantum wave, electric wave, whatever, it will have a frequency and a wave number if it's a sine wave. And there is a relationship that relates the frequency of the wave with the wave number. And what determines that relationship, that's basically the physical situation. In other words, the equation of motion gives the relationship between frequency and wave number. But whatever that relationship is, in this case, it's h bar times k squared over 2m. Whatever that relationship is, omega over k gives you the speed with which a particular harmonic travels. Now, here is what some people did. And again, I'm not scolding you. This is a great mistake to make, right? It's a fantastic mistake to make. We did take off one point to bring your attention to this. So what some people did is they said, aha, E. So some people did the following. So let me use a different color to emphasize it. So some people did the following. E, they started with 1/2 mv squared. That's 1/2 m times v times v. And I said, aha, this is 1/2 p times v. And the p equals h bar k. So they used the quantum p. And then they said, aha, v equals omega over k. And this is where they went wrong. I already kind of gave you a hint why this is wrong, because this is the speed of the wave, which is not necessarily the same as speed of the particle. But let's proceed to see what happens. If you plug and chug, you get 1/2 h bar k times omega over k equals 1/2 h bar omega, which is off from this expression by exactly a factor of 1/2. So there are two issues. Why is it wrong? And why it's wrong by exactly of a factor of 1/2. I will explain why it's wrong, and then you can skip over the second part where the 1/2 comes from. You know, if you're doing well in the class, if you feel like you're solid on your quantum game, you definitely want to listen to this where the 1/2 comes from, because it's not just where the 1/2, it's not a proof. Okay, it's not where the 1/2 comes from. It opens up a very interesting can of worms. But if you're not ready for that can of worms, don't listen to that, but at least listen to the next 2 minutes. Notice that omega over k, do you remember where this comes from? Well, you see, this is, let's see, 2 pi f over lambda over 2 pi. I'm sorry, 2 pi over lambda, pardon me, 2 pi over lambda. 2 pi over lambda, 2 pi is cancel. And this is lambda times f, which is equal to lambda over the period. Hey, that's equal to distance over time. So if you're finding speed by omega over k, what you're really doing is you're computing the distance per time. You're not allowed to compute velocity in quantum mechanics by distance over time formula. Why are you not allowed to do that? Well, because if you're measuring position here and position here, dividing by the time and calculating the velocity, that means you simultaneously know positions and velocity, right? That's how we find velocity in like introductory mechanics labs. We don't have a mechanics lab in this university, but what we do is we take measurements of positions, okay? We compute delta x, we divide by delta t, and that gives us velocity. That gives us the average velocity, but as we make delta t smaller and smaller, that average velocity approaches the instantaneous velocity. I'm mixing kind of a one-dimensional, two-dimensional thinking, right? So if you want, you can do delta r, right? And this way, we know simultaneously the position of the particle and its velocity, the position and its velocity. So to compute velocity using distance over time formula is equivalent to knowing position and velocity at the same time, which you're not allowed to do in quantum mechanics, because there's this basically an axiom that's called Heisenberg's uncertainty principle, that if you know position exactly, you don't know anything about momentum. I want to remind you, so this is a big no-no in quantum mechanics, okay? Due to Heisenberg uncertainty principle. Recall what velocity of the particle means. In quantum mechanics, it means nothing but P over M. So the rule is, you use the Broglie relation. You find the momentum. If you want, you can divide it by M and call it velocity. You're not really gaining anything from it, because velocity in quantum mechanics does not have this meaning. It does not have this meaning. It's better not to talk about velocity. Sometimes I talk about velocity, for example, when we talk about dust particle, but I didn't say that it's, well, you can still talk about velocity in order to estimate things, but it's better to just deal with momentum. If you want to talk about velocity, you must remember then that in quantum mechanics, it does not mean this, but it does mean this. This is not very useful. I mean, what you can define it like P over M. The only use of that is that as masses and distances and sizes of apparatus are increased such that you go into the classical regime, the velocity so defined will match with the classical velocity defined like that. Okay, I want to make sure that you understand what I'm saying. In quantum mechanics, velocity does not mean this. If you want to, you can define velocity like that, p over m. It's not clear what you're gaining from that because it doesn't have the meaning of distance per time. Okay, it's better to avoid the notion of velocity if you can't. For example, if you have to do an estimate, then you can do that, but you have to remember that really if we're in strongly quantum regime, velocity does not mean distance per time, it just means p over m. And p, well, what is p? What does measuring p mean? Measuring p means measuring wavelength. Remember, measuring momentum means measuring wavelength. Then if you want, you can define that momentum by m. That's fine, you can call it velocity. And the nice thing is that as you go into the classical regime, that will match with the classical notion of velocity. Okay, so you understand? If you want momentum, you measure the wavelength. Okay, you compute the ratio of h over the wavelength. That gives you the momentum. If you want, you can define by m, and that quantity will converge to the classical notion of velocity as you go to the classical regime. In other words, it will converge to the delta x over delta t. So what was your transgression? Your transgression was that you essentially calculate velocity you ascribed the velocity of the particle to this quantity. Now, I discussed that it's totally kosher to talk about speed with which wave functions move. Wave functions have a speed, okay? But that does not, it's not the same as the speed of a particle that the wave function represents. Okay, wave function, you can talk about speed with which the wave function moves. That's not the same as the speed of the particle. I think that this should be very important to note. Speed of the wave function, it's totally okay. If the wave function is a wave, the speed of the wave is, well, it's one wavelength per period, because as you see a wave pass by you, exactly one wavelength of that wave must pass during the time interval of during which any point on the wave goes up and down, exactly one cycle. That's where the lambda over t formula comes from. So this omega over k represents the speed of the wave, and it does not represent the speed of the particle. And moreover, in quantum mechanics, the speed of the particle is just p over m. It does not mean distance over time. Okay, that's why it was wrong to use lambda over t or omega over k formula. But why is it that you are, okay, so that's base. Okay, now you can listen, or if you want, you can skip. If you're confused, if all this is confusing, if you have a headache, if you just want to pass the class, if you're tired of all this, well, you can skip. Why the 1/2? Where does the 1/2 come from? Why are we off by exactly a factor 1/2? Now this gets into a finer issue. It turns out that this, right, after all, that's what this wave function represents, is not a physical wave function. It cannot represent a particle. Why is that? Well, let's see if we can remember that wave functions have to be normalized. What is the amplitude squared of this wave function? If we deal with this wave function, I don't know why this happens today. I'm having a very difficult day technologically, but if this is the wave function, you see this is the amplitude right here. Okay, so amplitude squared is a squared if a is real. So this is from -infinity to infinity, a squared dx. That's infinity, unless a is 0. But if a is 0, it means you have no wave function, you have no particle. You cannot normalize a plane wave. So even though a plane wave is a solution to the free particle Schrodinger's equation, it's not a solution that represents anything physical. To make it physical, it has to be a normalizable wave function. Hey, what if we have a wave function that's that tapers off at the ends. Okay, so it keeps its wave number or wavelength, but it just kind of goes to zero at the ends. This would be okay, and this is normalizable. But what does it mean to have a wave function like that? Okay, so this would be okay. Would be okay. But what does it mean to have a wave function like that? Exactly, it means you have to mix in more than one wave number. You have to mix in more than one harmonic. And each harmonic travels with its own speed, omega of k divided by k of that harmonic. So what this means in Fourier space, this means, okay, so you see this is not okay, this is okay. And you can make it arbitrarily big, right? So you can mix in just a little bit, but it has to be enough. It has to be a continuous set of harmonics. It doesn't have to be spread over a large wave number arranged, but it has to be continuous, right? And so if you do that, right, so in Fourier space, this is not okay. And instead, what you need to do is you need to introduce a little bit of a spread, okay? Tiny bit of a spread. It can be arbitrarily small spread, means wave function can be arbitrarily extended. As long as it's finite, you can always normalize it. Okay, and so you see these wings, these extra harmonics that you're mixing in, they can be present in tiny amounts. So this looks almost like a plane wave, right? So internal wiggles will have the wave number, basically what we started with, but we have to mix in a little bit of the wings in order to taper off this wave function, right? So you see these things, these mixed in harmonics make wave function go to zero at plus and minus infinity. All right, but then wait a minute. I just said each harmonic travels with its own speed, right? So each harmonic moves with speed omega over k. Let's see, omega equals h bar k squared over 2m. Remember, anything that satisfies free-particle Schrodinger's equation will have to have this relationship between wave number and frequency. That's h bar k over 2m. Maybe you see where I'm going. Okay, so if you were to simulate this, if I was to plot this mathematical, whatever, what you would see is the following. You would see that the wave packet as a whole travels at a different speed than the dominant harmonic or than any other harmonic. Okay, so here's the point. The speed of the particle represented by a wave packet wave function, arbitrarily large, almost a pure wave, but the speed of the particle represented by the wave packet wave function is given by the speed of the wave packet. And you might guess that the speed of the wave packet is the speed of the dominant harmonic in the wave packet. You would be off by exactly a factor of 2. Well, that's not supposed to be obvious to you. It comes from the theory of Fourier theory of waves. The speed with which the peak of the wave packet, the speed of the wave packet moves with a different speed than the dominant harmonic or any other harmonic. It turns out that the wave packet moves with speed given by the omega decay evaluated at the dominant. So it's not the speed of the dominant harmonic, but it's this concoction called d omega decay evaluated at the dominant harmonic. This does assume that you have a rather tight range of k's, right? If your range of k's is very broad, then it's not clear what you mean by a wave packet, because the wave packet will change shape. This is why relationship between omegas and k is called the dispersion relation. But that's going off the tangent. Okay, so I don't want to go there. Let's see, the omega decay, it's d decay of h bar k squared over 2m with h bar k times 2 times 2m, aha, equals h bar k over m. So the dominant harmonic travels with speed h bar k dominant over 2m. Any harmonic travels with speed h bar with speed h bar over k, and the wave packet overall, the wave packet of the overall travels with speed h bar k dominant over m. Okay, so this is the speed of the particle. So v of the particle is not equal to omega over k, equals 2 times omega over k of the dominant harmonic. Okay, and again, you can make wave packet arbitrarily large. You can compensate for that by making a as small as you want, but finite, and that will normalize it. But pure periodic wave cannot be a physical state. You have to taper it off at the ends. Note, yeah, and so that basically is the issue. So they were off by a factor of 2 because they used speed that's a factor of 2 smaller than the speed of the particle represented by this wave. Now, this is a really fine point. You could not possibly have known this. But I did say that, well, you calculate the momentum using de Broglie relation. You calculate the energy using de Broglie relation. You can define the speed using P over M, and that would match to the classical speed. Okay, so note, P over M equals H bar K over M does match this thing right here. You see? So like I said, P over M is correct. As you go into the classical regime, P over M does give you the classical speed that's calculated using dx dt. Also, if you use p squared over 2m, no, sorry, just a second, 1 second, let me pause for a second. What I wanted to say is that you will notice that the energy h bar omega, which is h bar times h bar k squared over 2m, which is h bar squared k squared over 2m. That's equal to 1/2 times m times v of the wave packet squared, right? Because this gives you h bar squared k squared over m squared, right? And then you multiply by m, gives you h bar squared k squared over m, and then times 1/2. And then you recognize that this is exactly like in classical formula, 1/2 mv squared. In contrast to if you use velocity not of the wave packet, but of the velocity of the wave, right? Of the harmonic, right? You would be off. You would get the wrong answer. You would not get the classical expression. That's what I'm trying to say. And therefore, so okay, so would not get 1/2 mv squared if use harmonic velocity. Okay. You would not get 1/2 mv harmonic if you substitute the harmonic velocity, right? So let's try that. So you go h bar times omega, so the h bar squared k squared over 2m, right? And harmonic velocity is h bar squared k squared over 2m squared. So that's 2 over 4. That's 2 m over m squared. That's 2 m times, just a second, I'm making a mistake, just a second. Yeah, so what I'm trying to say is that, again, e, h bar squared over k over 2m, you can write that as right, so this is h bar squared over 2m. You can write that as 2m h bar squared k squared over 4m squared, which is 2m times v of the harmonic, right? And you're off by a factor of 4 because your velocities are off by a factor of 2. So this does not equal to 1/2 m v harmonic squared. And that again supports that the wave packet velocity is what matches up to the classical velocity, because the expression looks just like the classical expression, while the harmonic velocity does not match up to the classical velocity. So as you go into the classical regime, the velocity of the wave packet will actually match up to the velocity of that classical particle that you can compute with dx dt. Okay, and again, it's what I said, that p over m matches up to that velocity is also true, because p over m is equal to the velocity of the wave packet. P over m is h bar k over m, which, like I said, matches up to the classical velocity. What's the moral? The moral is that you should start, the moral is that measuring momentum in quantum mechanics means measuring wavelength. It does not mean distance over time, times m. Measuring momentum means measuring the wavelength. Once you have the momentum, you can divide it by m and call it v. you're not gaining anything from that in quantum mechanics. But that number will match up to the classical velocity, that as you go into the classical regime, you make things bigger, you make things more heavier, it will match to the classical velocity dx dt as you go into the classical regime. The second point is that if you do represent particles by traveling waves, you cannot have a single harmonic. You have to mix in other harmonics to make it a normalizable wave function. And then when that wave packet wave function represents a particle, the speed of that particle is the speed of the wave packet. In other words, again, as you go into the classical regime and you measure the speed by dx dt, distance over time, that speed will match with the velocity of the wave packet overall, not the velocity of any particular harmonic, including not the velocity of the dominant harmonic.